So I was getting into spectroscopy and found this image with all the, spectral emission lines of each element laid out from lowest to highest mass. So going from one on the periodic table, just across the line all the way down, right? And they were all laid out. And I was looking at this image that I found. I was just like online, like on Google. And as I was looking at it, I kind of noticed like it looked like almost there was like an uptick and then a down and then uptick and then a down, right? Where there was higher and lower, emissions. And I was like, that's kind of interesting. And initially the way it was laid out, like it was like in rows. So it was like, here's one row, then one row, right? So they would all fit on the image because otherwise it would be really long, right? So I was like, well, I wonder what it looks like if they are just all lined up, right? In one row all the way across. And I don't know if anyone's done this. And I don't know if this is like big news or, been thought about, but I thought it was interesting. So I want to talk about it because to be honest, I don't know exactly where this goes. But I want to talk about it because it could potentially be interesting. So, I don't know if this is well known and it's not a big deal, but I thought it was interesting, so I wanted to bring it up. I was looking at and noticed that it seems to form a pattern. So I laid them all out linearly, and to me it looks like the visible spectrum. Not sure what this means after thinking about it exactly, but it's cool. This is just me like writing. After some more thought and information on black holes and star collapse or supernovae, it may be that atoms are actually just light or photons of a larger scale, hydrogen being the highest energy and lowest mass with the heaviest elements correlating to red wavelengths, which makes sense with my current theory. This puts mass on the spectrum in a way that I think makes sense and ties in the gap between seeing photons as massless and matter as having mass. It also works with my electron supernova photon emission theory. Looking at them all laid out in order, they radiate in different amounts that we would observe as quantitative waves at a smaller scale, just as we do. Just as we do. Sorry. I'm going to read that again. Looking at them all laid out in order, they radiate in different amounts that we would observe as quantitative waves at a smaller scale, just as we do. Larger emission spectrums result in larger distribution of the energy and a larger wavelength. This could also explain dark matter. This is a speculation here. I'm really not so certain about this part, but this could also explain dark matter, as some of these materials have very low emissions and would be hard for us to detect or see as a result. Maybe this plays a role in vacuum fluctuations, but this is getting progressively more speculative, so I'm not totally sure. Just putting my thoughts out there to potentially refine in the future. So one thing I will say is that all these videos are not saying this is definitely how it is. It's just me putting my thoughts to words, and I can come back on these videos, and as I speak on them, I think about it, and so it also helps me to kind of reflect and be like, does that really make sense? Does that seem right? So that's why I'm making these videos, and I can also then come back in the future and listen to it, and maybe it'll spark a thought or make me realize, oh, that was wrong, but this is why it was wrong, and kind of show my progression and keep track of what exactly it is that I'm laying out, basically. And so if you could see on here, that's the image that I'm talking about. That's what I found online. And it's just all of them kind of lined up in a row, right? And I kind of noticed it goes up and down, up and down. So I thought that was interesting. So I kind of put them all together, and I don't know if you can really see it all that clearly, but you can see that on this side over here, right, we have a small little bump for the smaller part of the spectrum. And then as we go out, this, I kind of drew it here, this wavelength gets larger, and like there's a bigger and bigger bump, right? And so what I think is interesting about this is because these there's multiple aspects to this, right? So as I said, hydrogen would be on the violet side of the spectrum, potentially into the ultraviolet, and then somewhere a little bit after hydrogen is where we would consider violet to be. And then we have different little points of waves and stuff. And so these waves that I've drawn out here, like, it's how we kind of observe the spectrum. And I think it's interesting, but I don't know exactly what these gaps mean when I'm looking at this. Like where the peaks are, okay, this makes sense. But where there's a dip, that is interesting to me, because it's almost like, okay, well then what is that? Right? So if I'm relating this to photons, right, we have the photons that are flying through, but then there's also the photons that we don't see that are flying through. And that is interesting to me, and it's kind of a moment, so I'm not totally sure what I'm trying to say here. I don't know if that makes sense to be what we consider dark matter or not. But if that turns out to actually be what dark matter is, which I'm not saying it can't be, but if that is what it is, then what I've been talking about as dark matter this whole time is not that. So what I was considering dark matter is really, it would need a different name then. So this is interesting, right? This right here would, like, you would have to call these dark matter. This would have to be what dark matter is. But it would make sense that we can observe dark matter, because on some level, because it's still technically in our relative frame of reference. And so we see matter, and then there's also dark matter. But it's just really interesting, because it would make sense that if it does not radiate, like if it doesn't have a large emission spectrum, we wouldn't be able to see it, because that's what we see. We see emissions. We see radiation. We do not see, like, if a mass does not give off radiation, we can't see it. And that is just like, it's like, duh, but like, that is really interesting, because there is matter that, looking at these spectral emission lines, give off very little emissions, and therefore would appear to have very little energy to us, right? These photons this matter, really it's more for photons, I guess, is where this is more important, because we do observe a lot of, if it has an emission, then we do observe it, right? But with photons, right, if you're thinking on the small scale, what I put there was that, there's the violet, then there's indigo, blue, green, red, orange, yellow, right? And so it looks like they all kind of just blend into one another, but there might be gaps there where there's kind of a dip, and there are these photons that are being given off that could be this quote unquote dark matter that we cannot see, right? Because these photons are they don't have a high emission spectrum. They have a very small emission spectrum, and therefore are basically invisible to us. And I don't know. This is really interesting because, like, then what? Like it just this is just very interesting because that could also be what dark energy is. Where it's like, oh, what's this dark energy? It could be this, these dark photons that are flying around everywhere, or like they could. I don't know. I don't know. It's very speculative here. I don't know exactly what this means, but I think it's very interesting. And I'm gonna just move on now to explaining why I'm so baffled by this, and it's causing a lot of confusion. Because when we look at this, when we look at the spectrum, we have wavelengths, right? And so we look at it and go, oh, that's red, right? And we think it's red because it has a large, wavelength. So it has a big arc, right? And so an atom that has a large amount of emissions would appear to have basically a larger arc. And because it's the thing is that, as I have said, not all photons are created equal. And that's not the current common belief, but I think that just makes sense, just logically, that not all photons are the same. But we will find out, I guess, right? So I think that it makes sense that not all photons are created equal. And so when we are observing this red wave, it is a wave of red photons, but this wave of red photons has photons that are at the peak of the red spectrum, and then those that are a little bit higher on the red spectrum and those that are a little lower on the red spectrum. And overall, it averages out to this wave that we observe like this, right? And we observe it as a really large distribution because there is a lot of variability and high mass to these photons. And so we get a broader spectrum, right? But then we look at something like blue or violet, and they have a smaller mass and a smaller distribution of and as a result they have a smaller spectral distribution and therefore appear to have a tinier tighter wave. And I don't know if what I'm saying here is right. It feels very interesting, and I feel like I have to talk about this because I don't know if this is like a well, discussed and thought about thing with these different, waves in the emission of particles or of atoms. But I think that this could be something potentially. It doesn't correlate one-to-one with what I've currently been saying because it really, I don't know. I feel like it could cause some issues with my current thinking because I don't know exactly what this means. I know that it is significant in some way. I have no idea where it fits into place quite yet. I think what I'm saying is logical. I think that it's a good direction to potentially take it. But I'm pretty much just putting this out here right now because I looked at it and I was like, what is this? What is this? But it's just interesting because, if I'm right about this, then there are photons that we can see and then photons that we can't. And I don't know, it just opens up the door to some weird things. And what I like initially said. Like I was like, it would kind of make sense that these photons are getting, like, their wavelength appears smaller because of length contraction, but I don't know if that is true anymore. Based off of this, like, that may not be exactly what the case is. Maybe that's still part of why it's like that, but I'm not totally sold on that anymore with this. This puts a hole in that, because it's like, if it has to do with length contraction, then why is there this distribution in the matter, right? Why does matter have this seeming pattern of distribution that would appear to be spectrum, like a spectrum distribution? And, like, I know that, like, there's probably a pattern that is, I'm assuming that this pattern has been observed and there's an explanation for it, but whatever the explanation is, I don't think it changes the significance of what this actually means, because it doesn't matter how you justify why it's that way. The fact that it is that way is what is interesting to me. I don't know. I just like tying matter back to photons. I think is like the ultimate checkmate, because everyone is saying that photons can't have mass, and then if we can prove that mass is photons, then that's a game over. They lose. But I don't know, right? So I don't know if that's actually what this means, but I feel like it would make sense. So I don't know, right? Just kind of thinking it out. And so, yeah, I wanted to talk about that. I think that's everything that I needed to say with this one. Yeah. Also, just a little tidbit I'll add on here, because I had a thought to myself was, what causes the color of metals, right? Why do metals have that weird, like, kind of shiny, gray sheen to them, right? So, basically, it's because of a majority of metals that have that appearance have the larger spectral lines of emission, and so they don't put off white light, because they do still absorb some of the spectrum, but they emit a large majority of it. And so you end up with this, gray color, which is kind of a mix between black and white. And then it's shiny because of the behavior of metals and how, reflective they are, and because of their density and things along those lines. But you don't really get that appearance unless you polish it up and make it like a smoother surface, so it's a little more uniform. Depending on the metal, of course. Not all metals are the same. But typically you get a better result when it's smooth and polished. But yeah. Anyway, so that's the answer to that question, in case you were curious. And yeah, I don't know. I just think that it's really interesting to see these distinct waves kind of pop up in the emission, like quantity and like levels. I don't know. I just thought it was really cool. So, peace out.